So yesterday we were seeing this example. I had taken a group G generated by an element little g of order 2. Okay, so it's cyclic of order 2. And we had employed the construction of permutation representations, which are just some special linear representation. So the permutation representation associated to the right regular representation of G. Note that this is something that has to do with permutations. What does it mean? That I take a vector space V, a vector space, so a C vector space. I don't think we will have vector spaces over anything else in this course. And with bases V1, Vg, where 1 and G are exactly the elements of this group G. And well, as I said, I want to give a representation, which means a morphism of groups from G to GLV. So of course, rho of 1 has to be 1 here, which is the identity matrix. That's trivial, it holds for all representations. Whereas what happens to rho G, where rho G sends V1 to what happens when you multiply 1 by the index 1 by G, the index being an element of the group, so to Vg. And it sends Vg to what you obtain when you multiply the index by G. So since G has order 2, you obtain V1. So in the basis, V1, Vg, rho G as matrix. I will be using this a lot, so let me go through the motions again. I have V1, Vg here, V1, Vg. I use row vectors, so V1 goes to Vg, which means 0, 1, so Vg, and Vg goes to V1, so 1, 0, okay? And that's a perfectly good representation obtained from an action of G on itself by right multiplication, okay? I said yesterday I should have put the inverse here instead of the element G, but in this case, G and G inverse are the same. Because, I mean, since this is a group of order 2, of course, the inverse of G is G itself. Now I want to explore, I mean, this is a particular case of something more general, but it's useful to do it in elementary fashion first. So we want to explore some sub-representation of this. Essentially, I leave this to you as an exercise to well, okay, although I'm doing part of the exercise myself, find eigenvalues, the eigenvalues, and eigenvectors for rho G. But I'm doing most of it, although I'm giving the result, particularly for eigenvectors, I'm giving the result without going through the theory. But I mean, it's nice if you apply the general theory that I learned in linear algebra instead. Anyway, what are the eigenvalues? So remember, this is important. Since G squared is 1, we have that 1, which is rho of 1, as before. 1, of course, is being the identity matrix, is rho G squared, but rho is a morphism, so this is rho G squared, okay? So rho G is a root of x squared minus 1. So its eigenvalues are a subset of 1 minus 1, okay? And remember, since the eigenvalues of these are distinct, it means that rho g can be diagonalized. So sorry, the correct form is this. So, this can be diagonalized, okay? Because the minimal polynomial has distinct roots as it divides the square minus 1. So can be diagonalized. And so you see immediately that the eigenvalues are really 1 is minus 1. Why? Because, I mean, if it has only eigenvalues 1 and can be diagonalized, then this should be the identity matrix. And the identity matrix looks the same with respect to all bases. And similarly, if the only eigenvalue is minus 1, since it can be diagonalized, it should be the minus the identity matrix. And again, this is not it. I mean, the minus the identity looks the same with respect to all bases. So the eigenvalues are this. So we expect to find eigenvectors with respect to 1 and minus 1. And I'll just tell you what they are. And then, as I said, you can do the exercise of finding them with a standard method, which is solving sublinear equation. And this is rather simple. Let me just see. Okay, I have 2 pages, blank pages. So, so you simply consider V1 plus Vg, okay? And you see, since what rho g, here it is, does is exchanges V1 and Vg, okay? If you take the sum, of course, this is fixed, because when you apply rho g, this is a linear map. So it's V1 rho g plus Vg rho g. And we have seen here that what happens, V1 goes to Vg and Vg goes to V1. And so this is nothing else than Vg plus V1, which of course is the same as addition in a vector space is commutative. And similarly, if you consider V1 minus Vg, okay, and you apply rho g, so once more rho g exchanges the two, so you get Vg minus V1, okay? And this is nothing else minus the original thing, okay? So, I mean, these are eigenvectors with respect to distinct eigenvalues, so they are independent. So, with respect to the basis, which we will call E1, say, V1 plus Vg, and E2, V1 minus Vg. Rho g has the form. We have diagonalized rho g. Rho g equals 1 minus 1, okay? And then you see what I was mentioning yesterday, that note that the subspaces W1 generated by E1 and W2 generated by E2 are invariant under rho g. Sorry, rho of capital G. Meaning that for I equal to 1 and 2, if you apply all the elements of rho g to Wi, you obtain Wi. This is clear because you see this is E1 and under rho g goes to E1, and this is E2 and under rho g goes to minus E2, which of course is in the space generated by the E2, which is just a set of all scalar multiples, okay? And so this means that you have subrepresentations, so you obtain subrepresentations. That is, you restrict rho g to to the two subspaces, and you obtain two maps rho W1 from G to GL W1. This is one-dimensional, so this is just C star, okay? I mean, if the space is one-dimensional, and rho W2, well, actually, C star, the matrix is saying one by one non-zero matrices, and from G to GL W2. And what are these? Well, it's very simple. So you have a one by one matrix. So rho W1 of G is just one. So it's just this piece here, okay? And whereas rho W2 G is just -1. It's just this piece here, okay? And we'll give a formal definition, but you see that we, in a sense, we have decomposed the formal definitions will come, but it's important to have examples at hand when the definitions come. So we have decomposed this representation into two representations of dimension one, okay? And later we will introduce a concept, a rather natural concept of direct sum of representations, and will turn out that the representation in dimension two is just the sum of these two. Okay, let's do a slightly more complicated example, and this time I'll use the same notation, hopefully without any confusion. This time this group is cyclic. Well, of course, it's cyclic, generated by G, of order 3. Okay. And so it consists of three elements, G square, if you wish, this is G inverse, it's very much the same. And once more, we first consider consider first we're talking permutation here, the right regular representation of G, so over itself. So this is the map so recall, this is a map from G to the group of, this is a group of permutation over S, over the set G, and set G to X is sent to XG, okay? And so you consider a vector space of dimension 3 with bases V1, Vg, and let's say Vg squared. So once more, this vector space is, this basis is parameterized by the elements of the group G. And so we now construct rho of G. It's enough to say what rho G is, because rho G squared will be just its square, but I will see what it is. How does it act? Well, you take V1, Vg, and Vg squared, and you send them in V1 times G. Well, I should take the inverse, because what I'm getting here is a right, is a left action, say, but since the group is abelian, it's really the same, okay? It's not, this is not important. So, because I mean, in the original definition of this construction, I put an inverse here, which would be perfectly correct, but for simplicity, let's do it here. I mean, it's the right action anyway. So this goes to Vg times G, and this goes to Vg squared times G, okay? So this is Vg, this is Vg squared, and this is V1. So in terms of a matrix, what do? I take a 3x3 matrix. As usual, the labels, I use labels for rows and columns that refer to the basis elements. And in the first line, I write the coefficients of the image under rho G of, so this will be rho G in this basis, of the image under rho G of V1. So this is Vg, so there's a 1 here and through 0. This just means, and I won't repeat it for the others, that when you apply rho G to V1, you'll get 0 times V1 plus 1 times, Vg plus 0 times Vg square, okay? And similarly, Vg goes to Vg square, so there's a 1 here and 2 zeros here. And Vg square goes to V1, and you get this, okay? And of course, when you do rho g square, it's just the square of this. And it's an easy exercise. Well, what happens here? Well, essentially, if V1 goes to Vg and Vg goes to V squared, then if you do it twice, V1 goes to Vg squared, this will go here, and this will go here. Okay, I'll leave this to verify. I'll leave this to you to verify. Okay, so we have this. But once more, with the same argument that we saw earlier, let me repeat it once. So since 1 equals rho g cube, this time g as order 3, rho g cube, rho g as minimal polynomial and I put divide in parentheses because it will be really s cubed minus 1 because it's a root of this polynomial. So its eigenvalues are a subset of 1 omega square, omega being a primitive third root of unity. So omega would be e to I to pi third, okay, with the usual complex exponential. And then I should check that in fact the matrix that I will repeat here has exactly these 3 eigenvalues, and we can find with the standard methods of linear algebra. I'll do it by hand, okay? First of all, exactly as so we should check that all eigenvalues appear, and we should find the eigenvectors. I'll do it directly. I mean, but you can apply the general methods, and it's quite obvious, as before, that this is fixed. Okay. Okay, and simply because what this matrix does it is to permute these 3 vectors. So of course you obtain them in a different order. I mean, you will obtain Vg plus Vg squared plus V1, but this is okay. And then I consider, so let's call this E1, okay? And then I consider 2 other elements which are natural once you do the standard linear algebra exercise. The first is this one. And let's see what happens when I apply rho g to E2. So rho g, what does it do? No, sorry. So it sends quite naturally V1 to Vg, okay? Vg to Vg square, and Vg square to V1. But look what it is. There's an omega square here, omega square, V1, plus Vg has no omega, so it's omega Vg, because omega squared times omega is 1. This is a third root of unity. And this has an omega. So if you put an omega square, you get an omega fourth, which is exactly omega fourth is omega, because omega 1, omega to the third is 1. So you obtain omega square E2. So we see that E2 is an eigenvector with respect to eigenvalue omega square. And similarly, if you consider E3, I should have given them in the opposite. Okay, sorry, I'm changing this, so let me do it in red. Let's call this E3, okay? Because it's more natural to. Actually, there would have been something even more natural. Well, calling this E2, this, well, okay, never mind. So this will be E2. And what's E2? It's a slight variation. No, sorry, this is V1. plus Vg plus omega square Vg, omega Vg square. And you check that if you apply E2 to rho g, you get omega E2. The right notation, it would have been to call the first one E naught, because the eigenvalue here is 1, which is omega 2, 0, and this would have been E1 and this E2. However, what's the point? The point is that with respect to the bases, E1, E2, E3, rho g has the form so you have two forms of rho g, because rho g depends on the basis. So 1 omega, omega square, okay? I'm not writing the zeros, okay? So I have diagonalized this as well. And of course, rho g square is just a square. So it's omega square, omega, okay? And once more, we find 3 sub-representations, okay? Because the subspaces, the subspaces Wi generated by EI are rho g invariant subspaces. And so I'm hinting at the fact that this representation is split into the sum to be defined of 3 one-dimensional representations. So I just mentioned that for abelian groups, this is always true, okay? So every, it's more complicated for non-abelian groups, infinitely more complicated, but every representation, representation of a finite abelian group can be split into the sum of one-dimensional one. You see 3 boxes here, 2 boxes before. It's a general fact. We'll get to there. Okay, good. And now, remember that I started yesterday's lecture by recalling that you can define actions in 2 different ways, either axiomatically or as morphisms. So remember, one definition of action was a morphism of G into S omega, the group of permutations on a set omega. And a representation, remember, representation for me is short for linear representation, is a morphism from G to GLV. So in both cases, I represent through rho the elements of G, here as permutation, here as, say, matrices, linear maps. But there was another definition, as I said, of action, which is axiomatic. And I want to see what the corresponding concept is on the right. And so let us introduce the group algebra. Maybe you've seen it already, but... oh, I have a question for you. You have seen modules over rings, right? Essentially, if... okay. If I get no answer, I assume that all of you have seen those. Okay, so what's the group algebra? Well, I think you should have seen, at least if you've taken algebra with me, the construction of polynomials. Okay, I'll start with recalling the construction of polynomials, because the group algebra construction is in a sense based on that one. So remember how you construct polynomials. You consider, let F be a field. Okay, any field. Okay, consider the set of say of maps, we will call F, from very well, okay, to N to F, which are eventually 0. which means that for any f, there is given f, there is an n such that f I equals 0 as I is greater than n, okay? So not all maps from the natural to f, but those that become 0, that vanish after a certain number. This number can depend on f. And then you sum these maps pointwise. So this means that f plus g in a natural I is just fi plus gi, which means essentially that you can represent f through a sequence or a vector of its values, f naught, f1, f2, and so on. And so you sum these vectors, okay? Oh, well, okay, fine. And then how do you multiply them? And then you multiply two of these maps with the convolution product. Which means that f star g of I will be what? And this is important because it's is the sum of fs ft gt, okay, where s plus t equals I, okay. And why is this convolution product, and you will have seen it also in probability, for instance, in analysis. Why is this convolution product natural? Because this is how you multiply two polynomials. So if this vector here really represent a polynomial, let's say a naught plus a1x plus a2x squared and so on. And if g is b1 plus b1x plus b2x squared and so on, how do you multiply this? So what's their product? The product is a naught b naught, and then a naught b1 plus a1 b naught x and so on. I mean, this is something we learn in school, okay? And what's the point? The coefficient of, say, x squared is given by the sum of all products of, these are not the value of the polynomial, these are essentially the AI, okay? This is like AS and this is BT, where the sum of the indices equals, in this case, 2. I mean, here the sum of the indices is 1 and so on. And so this is a construction. I won't go through all the details, but this is how you construct polynomials, okay? So the convolution product is nothing else than the usual product of polynomials. Now, with the group algebra, for simplicity, I will do the group algebra of a finite group G, although you could consider group algebras of any group. I will mention how you do that, but it's quite obvious over C, although you could do it over every field, really. But I mean, we are all interested in this one. And this is the set of maps. So this is usually called, let me check, this group algebra is called, wait, just a second. Is denoted as C of G. There are other symbols in the literature, such as CG without the parentheses. And this is the set of maps from G to C, okay? This is because the group is finite. if I have an infinite group, I want to write it down, but it's then you do exactly the same as I did for polynomials. You take the map that are well, there are almost everywhere 0. Okay, there are 0 of finite support. Okay, there are 0 outside a finite set. Okay, but I mean we don't need not to consider that. Consider a set of maps. This is not only an abelian group, but it's a vector space. If you do things over the image. As usual, I mean, if you have a set of maps into a vector space, it becomes a vector space. If you, so you have 2 of these maps, let's say F1 and F2, and you do the linear combination. So these lambda I are in C, and these are 2 maps there. What's their value on element G? Simply lambda 1 F1 of G plus lambda 2 F2 of G. The same applied to the polynomials, of course. So you do it by using the image, okay? And it's quite clear that this is a vector space of dimension, the order of G. We'll mention a base, explicit base soon. I mean, it's always like that. If you have a finite set, you consider the maps to a field, you get a vector space with this operation, which has exactly, as dimension, exactly the order of G, okay? How do you define the product? Well, you do exactly the same. That's why I reminded you of what happens in polynomial. And then you take the convolution product. So if you have F1, F2, I try and avoid using F and G because G is a group element. So what's its value on G is the sum of all F1x, F2y, where the product xy equals to G. Now, a little technicality. I find very convenient this formulation for the convolution product, in which you have the absolute symmetry between the two factors here. There's x and y, and the product is G. Of course, you may say, look, G is fixed, okay? If you consider a fixed value of G, then x and y are not independent, because once you have chosen y, x, then y is nothing else but x inverse G. So you could rewrite this, if you wish, as a sum where x ranges in G, and you have F1x and F2, if I'm not mistaken, yes, x inverse G. And this will be perfectly fine. Yes, you can recognize this because the product of x and y has to be G. So the product of x and this is G, okay? But this asymmetric form is less useful when you want to do proofs. I mean, that's my experience. So for instance, a hint at the associative law, at associativity. I mean, this product I claim is associative. Okay, how do you prove this? Well, you have 3 maps. And you first do this product and then this one, and so you apply it in G. Okay, so you have the convolution of this map and this map. So by definition, this is the sum, and here I have to choose the arguments carefully. Yes, okay, so I'll say T Z equal G. As you see in a second why I'm choosing letters like this, where I have the first map computed on T, and the second map computed on Z, okay? Because I mean, this is the first operation I have to take. And then I have to expand this. And what's this? Is the sum over xy equals T of F1x, F2y, okay? So there are 2 sums, but you see that you don't need T anymore because T after all is xy. So you are summing over x, y, z in G. That's why I chose letters in this way. and you simply have f1, f1, x, f2, y, f3, z. And clearly, if you do it the other way, you get exactly the same, because after all, you get the sum of all product of this kind. So this is particularly easy to do if you use the symmetric form. If you use the asymmetric form, which might look better, because after all, there is only one variable here, and there are only two variables here, because, sorry, but of course, I forgot to say that x, y, z have to be g. I mean, this is correct, but I need to say that the product of the three is g. Of course, here too, you can choose x, y as you wish, but then z is dependent on them. But the reason why this works better, if you use this, you will need to, the asymmetric form, you will need to do a change of variable. And I mean, of course, you can do the change of variable, but if you use the symmetric form, you won't need to do any change of variables. So this is a hint at the associativity. You do it the other way and find exactly the same. I mean, just this very symmetric form. You can also show it's not difficult, because I mean, you have just a product in C here, that the distributivity law also applies. Okay, and so what you obtain with this operation, so let's say plus and star, CG becomes a C algebra. You can find something about C algebras in the preliminaries, but essentially these are rings. Basically, a ring. I'll try and write it better. Which is also a C vector space, plus some compatibility conditions. Essentially, the compatibility condition is this, that if you take, I'll write, if you take two elements and lambda, so lambda is in C and A and B are in this algebra, when you take the product in the algebra and multiply it by a scalar, it is exactly the same as doing this, or if you prefer doing this, okay? And yes, okay, well, there's something more, but you'll see the preliminaries. So that's a C algebra, okay? Slightly more there, it's a ring plus vector space plus something else. Good, and I mentioned a basis earlier, and here's your basis for G in G. Consider the maps, the elements of CG, which, recall, are just maps from G to C, defined as following, is the Kronecker delta, okay? So delta G of X is 1 if X is G, and 0 otherwise, okay? So it's a typical Kronecker delta, because it's only 1 when G equals X, okay? When X equals G, actually, because G is fixed and then X is the variable. And you can see that if you have any, say, any element A of the group algebra, then A is the sum for G in G of A of G delta G, okay? How can you see this? Well, because if you, these are functions from G to C, okay? So let's put a question mark here. If you compute the left-hand side on X, you get AX, okay? What happens when you consider, when you compute the right-hand side on X? okay, on a certain x. Well, delta g is always 0, except when x is g. So the only term that survives will be ag delta g, because all the rest are 0, and this is exactly ag. Well, sorry. When x is g, well, of course, sorry. It's yes, g is a dummy variable. So the only term that survives is ax delta xx, and this is exactly ax. So these two functions, this function here and this function here, have exactly the same value over all x. Okay, so they are the same, because we are talking, this CG is just made of maps from G to C. And so every element of CG, of the group algebra, can be written as a linear combination of the delta G. We already saw that as a C vector space, delta G has dimension the order of G. The delta G are exactly, since you have a delta G for every G, are the right number, okay, are exactly of the right number. So let's put it like this. So the set of the delta G, G in G, is a system of generators, of linear generators. Okay, no, I'll write it. I'll spell it out. Of generators of CG as a vector space, okay? And since this set, let's call it B, since this set is exactly the order, the elements of G, which is the dimension of CG, B is a basis of the C as a vector, or CG as a vector space, okay? But in practice, the delta G are not written delta G, and the reason is that if you consider G and H in G, okay, then you can consider the convolution product of delta G and delta H. So you compute it in X. What's this? Well, this will be the sum over all ST will give you X, okay, of what? Delta G of S and delta H of T, okay? But remember, these delta are Kronecker delta, so they are always 0, and so you have sum of products. The only way to have one of these terms different from 0 is to have both terms different from 0, because otherwise, if one of them is 0, the product will be 0. So this will be, if it is different from 0, it will be 1, if and only if S equals G, okay? And similarly, this will be different from 0, only if and only if T equals H, okay? And so you see that the only X for which there is a term different from 0 is when S is G and T is H, so when X is GH. So this will be exactly delta GH. Because you see, the only summand here, which is different from 0, you obtain when S is G and T is H. That is when X is GH, okay? So you see what, well, this is actually delta GH of X, because delta GH of X is the map that is only different from 0 when X equals GH, okay? And this is what we are finding here. So what you see that the delta G multiply under convolution exactly as the elements of G. Because the convolution product of delta G and delta H is delta GH. In a sense, you may say that the map from G, okay, to B, okay, which sends G to delta G is an isomorphism between G, the groups, G with its product, which normally goes unnamed, and B with a convolution product. Because I mean, the convolution product delta G and delta H is exactly delta GH. So this means this is an isomorphism. This means that in practice, in the literature, you will find CG defined, say, as the set of linear combinations, say something like AGG, G in G, where AG are complex numbers. So the idea is instead of writing AG of delta G, the people usually write AG use indices, but I mean, this is just a matter of preference. Instead of writing A as a function computed in G, you write the argument as an index. But instead of delta G, you write G, because after all, the product is the same, okay? Where the sum is component-wise, with component-wise addition. I mean, and the product, there is a bilinear extension of that of G. What does it mean? Let's take a concrete example. For instance, suppose that G is my group of order 3, okay? So what happens when you multiply 1 plus G squared by 1 minus G, okay? 2 elements of this form. So you simply do all the multiplications, okay? So, I mean, apply the distributive properties. So you get 1 minus G plus G times 1 minus G times G plus G squared times 1 minus G squared times G, okay? So I have just applied here the distributive property and then do the multiplication in G. So you extend bilinearly, which means you apply the distributive property twice, the product of G. And so what we obtain is 1 minus G plus G minus G squared plus G squared minus 1, because G cube is 1. And of course you get 0, but you see, because 1 cancel with this cancel with this, and this cancel with this, because this is a product, okay, a well-known product, okay. So that's in practice as you work with the group algebra. The elements are formal, say, linear combination of the elements of G, but remember that we have a definition through these functions, okay, and then you simply distribute and multiply as in G, okay. Now remember that the polynomials have a certain universal property that is essential when you study simple extensions. That essentially, once you have chosen, I mean, to give a morphism from a ring of polynomials to another ring, you simply decide where the constant go, and you decide where the x goes, and the rest follows. There is a similar universal property for the group algebra. And this says the following. So this is proposition. At the moment in the notes, this is 573. So let G be a group, and A be any C algebra. Okay? So a ring, which is a vector space with that compatibility condition. In applications, typically A will be the ring of, say, n by n matrices, C matrices. Okay, we'll see in a second as this works. So if you don't want to think in terms of an abstract C algebra, think of the ring of n times n C matrices, matrices with coefficients in C. Okay, let rho from G to A be a morphism of groups, say? Well, okay, let's say a morphism of groups. This is slightly inappropriate, but we'll see what they mean in a second. Then there is a unique morphism of algebras, of C algebras with unity, rho prime from C of G to A that extends rho. So think of this as an analog of the universal property of polynomials. You just need to decide, you have polynomials on one side and a certain ring on the other side. You just decide where the constant go and where x goes, and everything follows. And here what you're saying, you just decide where the element of G go, where they have to go through a morphism of groups, and then the rest follows. The proof, I will just give a sketch, but the idea is that you are really obliged to choose rho prime, because as we said, now we can say that the elements of the group algebra are just linear combination of this form, okay? And so if this has to be a morphism of C algebras, this respects both operations. Here we have sums and products, okay? So and if it's a morphism of C algebras, this means in particular that under this, lambda will go in lambda if lambda is an element of C. So a morphism of C algebras with unity, well, okay, means that the constants go to the constants. So what do you have here? You apply rho prime. So this goes through the sums and the products. So you will have the sum as G in G, rho prime of, sorry, AG, rho prime of G. Okay, so let's look at this. I mean, it's absolutely, if you check the proof for polynomials, you will see that it's very similar. So we have said that a morphism of C algebras has to send constant to constants. And these, of course, are elements of C, okay? So you obtain AG, and we want this to extend rho, which means that that on G, on the elements of G, rho prime, the values of rho prime are exactly the values of rho. And it's not difficult to see. I'll leave as an exercise that has to be done once in life. This is, in fact, a morphism of algebra. Why do we want to do this? Because the situation you want to consider is the following. Our application. Let G be a finite group. Sometimes I won't even mention this because our G are always finite group here. And V a finite dimensional vector space. Okay, I'll shorten like this: finite dimensional vector space over C, of course, because there won't be any other fields here. And let rho from G to GLV be a representation. Okay, but of course, GLV is contained in well, okay, I'll write it like, it should be the endomorphism of V. Okay, the C-linear endomorphism. Let's say this is the ring of n times n matrices over C. Okay, once you have chosen a basis. Okay, so these are invertible matrices. Okay, the invertible matrix will live inside all n by n matrices. So this is an algebra over C, a ring which is also vector space, and this is a group. Okay, so you see, you have a morphism from rho from G into this algebra, a group morphism. I mean, which means you respect products, inverses, and one. And then the proposition I gave you, this tells you that then there is a unique. This can be extended to a unique morphism of C algebras rho prime from CG to the, okay, let's write C. Okay, these are the linear maps, okay, ring of linear maps, of all linear maps on V. Okay, so these are invertible and these are all linear maps. Okay, here the C is intended. I mean, okay, so you have a morphism of C algebras from this to this. And if you have any problem with what I'm going to say next, just let me know now or by email or something. If you have such a morphism, this gives the vector space V, the structure of A CG module. Because one way of defining modules, I'll write it down in a second, and it's also a definition I tend to use, well, in higher courses like this for vector spaces. Yes, you can give all the axioms, but after all the axioms boil down to saying that you have a morphism of algebras from the ring of which modules are constructed into the endomorphisms of the module. So recall, I'm now doing the definition not in terms of C algebras, but simply in terms of rings and abelian groups. If M is an abelian group and A is a ring, then a structure of G module, then a structure of an A module over M, for M, is equivalent to given by a ring morphism. Here I have C algebra morphism, but morphism from A to the endomorphism ring of M. This is the endomorphism ring of the abelian group. So a compact way of saying what a module is, you have an abelian group, you have a ring, and then you define a structure of an A module for M as a ring morphing from A to the endomorphism of M. For instance, if A is a field, then here you get a vector space. If you've seen this before, I mean, the fact that this is a ring morphing from A to the ring of endomorphisms of M gives you all the axioms in a compact way. If you unwind this definition, you'll get exactly all the axioms. For instance, if you do it with a field here, you get the vector spaces. Okay. And so, if I do it with C algebras, which is slightly more general than the ring, this gives to this vector space the structure of a module over CG. Okay. And so we see that if we have a representation of G, then we get a structure of CG module over V. I'll be explicit in a second. So if rho is a representation, remember this means linear representation. We obtain okay, no, this gives to V, to the vector space, the structure of a CG module. And the structure is absolutely clear. Let's be explicitly. If V is in V, and I take an element in the group algebra, CG, okay? So all these AG are coefficients, okay? The structure of a module means that these are, in a sense, the scalars, okay? And these are vectors. So the standard definition of a module requires you to tell you what's the product of a vector by a scalar, okay? My action are right action, so this means I have to define what this is, okay? So how does this act on this? What's the vector times scalar? And the idea is the real scalars, there is the element of C, you know what they do, because they simply, this is a vector space product, okay? V is a vector space. And then how does G act? Well, G act via rho G, okay? Just a second, I'll be back in here, because I start with a representation. And so here I'm forced to say what does G do to V? Well, it does what rho G does, because rho G, remember, is an element of GLV. Okay, so it does something to V. Okay, sometimes one does not write rho G, but it has an action in mind. You see, when you consider action, say via permutations, you simply write, you don't write the map acting, you simply write alpha to the G. So sometimes you may find just G here with an action. I mean, the way the elements of G are thought as elements of GLV is understood, but I mean, I'll try in general to do this. And I can put parentheses here, but this is a linear map. So it's really the same whether I put the parentheses outside or inside. So this is a very convenient factor. So there is a dual approach. You may have a representation, and you may have, if you want, a G modules, a CG module structure over the vector space, and it's the same. Oh, the converse also holds. Conversely, I'll put this as an exercise. Conversely, a CG structure, a CG module structure on V yields a representation of G on V. Okay, so the two concepts are really equivalent. Either a representation means a morphing from G to GLV, or a CG module structure on V. And why is this C module structure particularly useful? Because, for instance, remember that I have given the definition yesterday, and then I have recalled it at the beginning of our lectures. Suppose rho from G to GLV is a representation. This will be my standard language basically from now on. So I intend that G is a finite group and V is a finite dimensional vector space over complex numbers. So suppose this is a representation. Let W be a subspace of V. Then we said that we defined W to be rho G invariant. If W rho G is in W for all W in W, and G in G. But another way of stating this W is a CG submodule of the CG module V. So it's a more compact way of doing this, because if you say CG submodule, it's invariant under the multiplication by element of C, so it's a subspace. And then it's invariant under, you will see this in a second, the multiplication by elements of G, so it satisfies this. Why? Because I mean, for W to be a submodule, well, no, let's do it in the other direction. And I'll leave some details to you. If the subspace W of V is rho G invariant, then it is a submodule. In this sense, a CG submodule of the module of the CG module V. How do you prove this? Well, you take W, little w in big W, and then you apply to this an element of the group algebra. So, okay, this is a linear combination, formal, but we've seen how it is constructed, a linear combination of this with elements in C, okay? This is defined, see previous slide, as the sum for G in G of AGW times rho of G. But you see, W is a subspace, so this is still in W, and W is rho G invariant, which means that once you apply to an element of W rho of G, you're still in W. So this is an element of W, because you're applying rho of G to an element of W. So you see that W is invariant under scalar multiplication, say, by element of the group, elements of the group algebra, and conversely. So you see that the language is somewhat simpler. I mean, you have to pay a price once to introduce the group algebra and the module structure, but then to say that this is rho G, a subspace with rho G invariant, simply means a submodule, okay? So it's a simpler, a more practical way of looking at things, and we will be using this terminology. We will be using this terminology soon. Good, there is something about the center, but we'll do it later. And now let's introduce an important tool. But first, we'll go back a second to our back to groups, even soluble groups. This is an example that I don't think I had mentioned. So we have spoken of composition series, okay? So composition series means a series in which cannot be refined. So if I take S3, okay, I have this composition series 1, generated by 1, then A3, and then S3, okay? And I write here 3 and 2, meaning that, say that the order of A3, which is of course the order of A3 over 1, is 3, and the order of the quotient group S3 over A3 is 2. If you consider a cyclic group of order 6, so suppose it's generated, for a change, let's be generated by S, okay? No, well, S is bad. Okay, it will be G, okay? Then you have 1, and then you have the group generated by G squared, and then you have the whole group generated by G. And once more, this is order 3, and this is order 2, okay? So the order of G squared, which is the same as the order of the subgroup generated by G squared, is 3, and the order of G over G squared is 2. So what you see is that if you look at the factors of the two compositions, series are the same. the two composition series of S3 and C6 are the same. Because of course, these are cyclic of order 3 and cyclic of order 2. Yet the two groups are not isomorphic. So unfortunately, knowing the composition factors, the isomorphism type of the composition factors, is not enough to decide the isomorphism type of the group. There is in fact a problem that is the isomorphism, say the residual isomorphism problem. Well, okay, no, well, let's write it correctly. The isomorphism problem from group extensions. Which means, just a short mention, which would mean if you know the composition factors, what about the group? And this is immensely complicated because even if you consider a P group, a finite P group, in which, if you remember when we talk CILO subgroups, which means that all composition factors are the order of the same prime P, you can have a very large number of groups with exactly the same composition factor. So that the number of groups of order P to the n, okay, grows exponentially with n for fixed prime, even if the composition factors are all of order P for all of them. So the isomorphic problem is very complicated because knowing the composition factor tells you something, but not too much about the group. Luckily for us, the situation for representations is simpler, because we are going to prove an extremely important theorem due to Maschke, which tells you, I'll state it in two different ways, okay? So that we have a chance of becoming familiar with the two languages. So as usual, I'll simply start by saying that rho from G to GLV is a representation. Once more, and then I'll stop reminding you of this, but G is a finite group and V is a finite dimensional vector space over C, okay? Suppose U is a rho G invariant subspace of V, okay? Then the important claim is, then there is a rho G invariant subspace of subspace W of V, such that V is the direct sum of U and W. There's no need to say everything at once, but it is exactly the situation that we've seen in the examples. For instance, when we consider the particular representation of the group of order 2, there were exactly two complementary subspaces, the one generated by V1 plus Vg and V1 minus Vg, complementary subspaces, direct sum, okay? This, of course, does not hold in groups, because let me be back a second, because if you consider S3, it has a normal subgroup A3, okay, which means a subgroup is invariant under, say, inner automorphism, but there is no complement. It's not a direct product or direct sum, whereas in C6 it is, okay? So in groups, you cannot hope to have this. This is not a direct product. S3 is just semi-direct product. But with representation, this holds. Of course, you know that these results holds for plane vector spaces. I mean, if you have a vector space and a subspace, there is always a complementary, say, subspace. But here we are telling more, because we are saying that this, if you have a rho G invariant subspace, then you have a rho G invariant complement, okay? This becomes probably slightly easier in terms of modules. So let us translate. A representation means let V be a CG module. So I have translated, let me use colors. This is the first statement, which is translated in 1 prime, okay? Let U be a CG submodule. Sometimes I will say a submodule. And this is the translation of the fact that U is rho G invariant, okay? So this is 2 prime. And then the statement is then there is a CG submodule W of V such that, and the same statement holds. And so if you call this 3, this will be 3 prime. So in a sense, this tells you that that the representation, CG modules, are not terribly different from vector spaces, okay? Because this, of course, holds in vector space. I mean, you have a subspace U of a vector space, finite dimensional vector space V. You take a basis of this, extend it to a basis of the whole group, and you take the element of the basis of V, which are not in U, and they form a complementary subspace. So this holds also for representation, although for representation is slightly more complicated to prove. And this can be formulated in terms of modules, I say, and if you formulate it in terms of modules, I think it should be clear how this generalizes the cases when you drop the G and you get just C module, which means a vector space, C submodule, which is a vector subspace, and another subspace, okay? So let's see the proof. This is so important that I will give it, I will get 2 proofs of it. I hope to be able to give the first proof completely today, but I'll stop at 4 anyway, and then I'll resume it and recall where we were next time. But let's go with absolute ease on this proof. So what's the situation? You have a representation rho of G to GLV. And U is a rho G invariant vector subspace of V. So remember, this means that U rho G is in U for all U in U and G in G, okay? And so the trick is the following. First, consider the situation from the point of view of vector spaces, okay? So you have U, which is a vector, a subspace of V, okay? And so it has a complement. So let X be a subspace of V, which is a complement to U. And I have recalled how you build it, but this is a linear algebra. So we have V, which is the direct sum of U and X. Of course, at this stage, we know that U is rho G invariant, so this holds, but we don't know anything about X. I mean, we just took X at random. We cannot expect to be that lucky. I mean, we don't know why you should be lucky. And then we consider the projection pi from V, sorry, this is V to U along, okay, let's of V over U along X. I don't know whether this is the right terminology, but what does it mean? It means that when you apply, and I'll write the maps on the right, when you apply this to U plus X, where U is in U and X is in capital X, the fact that this is a a direct sum means that every element of V can be written uniquely here. So I can define the pi separately on the two, and this is simply U, okay? So it's not only a projection of U, but essentially what I'm saying that U is the kernel of pi, okay? Because when this is zero, exactly when U is zero, that is when this element is in X, okay? So it has image U and kernel, so U is the image of pi, and the kernel is exactly X. Good. Okay, and of course, U of pi. This will be important. So we've seen that this is the kernel because when U is zero, you get zero here. And note that U pi equals U for U in U. Okay, a typical projection. Now we do a trick which is extremely important that we've seen before. We consider the map C on V, which is the following. Leave a space here because I'll construct it step by step. I consider pi, okay? And then I put the rho G here and the rho G inverse here. Of course, I can put the inverse outside or inside because this is a morphism. I do a sum over G. And then, since we are on the complex number, I can take the average. I'm summing over G, I can take the average. The average is extremely important. You can consider representations over different fields. For instance, a field with P elements, like Z over PZ. And then things fall apart because, I mean, if you are in the complex number or rational number, you can divide by any number different from zero. But of course, if your group has order divisible by P, then if you're working Z over PZ, the order will be zero in the field, so you cannot divide. So this makes the representation theory over fields like the field with P elements completely different and extremely more difficult. And I'll show you with an example, not this time, but next time. So what does this map do explicitly? If you apply psi to an element V of V, you have this in front. This is a constant, of course. And then what you do, you apply first rho G inverse, then you apply pi, and then you apply rho G. Okay? So it's a composition of maps, composition of linear maps. Of course, since rho is the representation, this rho G and rho G inverse are linear maps, but also pi is a linear map. But, well, this is obvious from the definition here. Good. So this map. And this map has several interesting properties, okay? The first property is, note that for all V in V, we have that V psi is in U. So remember, I had taken U to be the direct sum of X, and remember that pi goes from V to U, and said U plus X in U, okay? So this is our situation. Why is it so? Well, the reason is simply, well, this is a sum. So if I show that all summands are in U, I'm done because U is a subspace. So, and then you multiply by a scalar, it's okay. Let me first state it and then I'll write it down. You apply to V this rho G inverse. This is still an element of V. But once you apply pi, you end up in U, okay? Well, I should, let me rewrite this correctly because there's not much difference between my V, okay, and my U. This time it should be clearer. So this is simply an element of V, but once I apply pi, I get into U, okay? So this is an element of U. And remember, our assumption is that U is rho G invariant, okay? So this element is in U because I applied pi, and pi has image U. Once I apply rho G, this also is in U, as U is rho G invariant. Okay, so this is interesting. The image of U of V is in U. So if you want to write it globally, the image is contained in U. But my last claim, well, let's see whether I can do something else. Claim the image of Psi, this is the image of Psi, is exactly U. It's not only contained in U, but is exactly U. And the reason is rather simple, because I claim if U is in U, then U Psi is U, okay? And then of course this means that you can obtain all elements of U as images under Psi of what? Of themselves. And the reason is very simple, because what's U Psi? So this is what you obtain by taking U, applying rho G inverse, applying pi, and applying rho G. And then you sum over all this and you average. But you see, so if you start with U in U, this will be in U as well. It's the same reason I write it here, because U, so the red fact is because U is assumed to be rho G invariant. So invariant, and of course, rho G inverse is nothing else but rho G inverse. Okay, you can put the inverse inside. So this is an element of rho G. Okay, so rho G invariant means that you take an element of U, okay, you apply an element of rho G, where this is an element of rho G, and you still stay in U. Now remember, pi is the projection on U. So if you take an element of U, pi sends it to itself, okay? So this means that this equals, once you apply pi to this element of U, you get the element, that same element, okay? Because pi sends U plus X to U, if U is in U and X is in X. And of course, here you have rho G inverse and rho G. So this is what this is. This is 1 over G, and then the sum G over G of U, because rho G inverse and rho G, of course, cancel out. And of course, you're summing over G. There's no G here. So this is simply 1 over G. These are order of G factors U, and this is just U. So we have seen that U of Psi is U, okay? And what I claim, now, okay, fine, yes. So we've seen that, let's state where we are. So we have seen that we have a linear map Psi from V to U, such that the image is U, and actually for U in U, we have U Psi equal U. Consider oh yes, okay. So this means is an idempotent map. What does it mean? It means that if you do Psi square, which means Psi composed with Psi, you obtain Psi again. Why is it so? Well, it's simple, because you have an element of V, and you apply Psi square, which means this is the composition. So you apply Psi, and then you apply Psi again. But we have seen that the image, once you apply Psi, you obtain an element of U. And we've seen that if you take an element of U and apply Psi, you get U. So this is an element of U. This is so important that I'll put it in red. Okay, so the image is in U. And then if you have an element of U, U psi is simply U. We just proved it. So you have this element of U, you apply psi, and what you get the same element of U. This is for all element of V, so psi square and psi do exactly the same thing. This is equivalent to saying that psi square equals psi. And this is something we learned in linear algebra, but you can find it in the preliminaries if you need to refresh this. So since this is an idempotent, we will have that V is the direct sum of the image of psi and the kernel of psi. This is an elementary fact. This we know to be U, and what we'll prove that this is Rho G invariant. And so we will find our result that we have split V as a direct sum of U and the vector space, which is Rho G invariant. And this will be the content of Maschke's theorem. But that's all for today. Thank you for listening and see you next week. Remember, anytime you can write me and we'll fix an appointment in this Zoom room. Okay, thank you. Bye.